We've talked about aqueous solutions for a long time now. Back in first term, when we were doing reactions, we learned about reactions in an aqueous solution where we would have precipitation reactions, single replacement reactions, things like that. And then in second term, when we were learning about stoichiometry, we learned the basics of solution chemistry, and particularly we talked about concentration and molarity and things like that. Some of these slides today are going to look pretty familiar. We've talked about them before. The basics of solutions being homogeneous or homogeneous mixtures, where you have solvents, which are kind of best defined as the particle or the molecule that is in greatest quantity, or the number of particles that you have is greatest. And then solute, where you have something that is dissolved in the solvent. It is going to be the particle that we have less of or fewer of. So in this context of this solution right here, we have more water molecules surrounding carbon dioxide molecules, water being the solvent and carbon dioxide being the solute. We also talked about hydration or solvation, the process by which, if I have a solid like salt, this is salt, and it's supposed to be solid down here because it's has that nice crystal lattice structure. The process by which water would dissolve that salt is that water molecules would essentially pick apart the solid and start to surround particles. And water is itself very versatile in its ability to do some dissolving. So we can have the hydrogens, water's polar. The hydrogens are the positive end of the water molecule. They're really good at dissolving negative ions within that salt. And on the other side of that, we can have, if I look right here, I can have the oxygens oriented towards the positive ion in a salt and surround them. Anytime you see that surrounding process, that's called solvation. And when in particular we have water doing it, it's called hydration. We've really never talked in depth about that interaction right there. These are a type of intermolecular force, actually. We call them ion-dipole interactions. So instead of like dipole, or ionic bonds, this is really an ion-dipole interaction that's taking place during that solvation or hydration process. What we haven't talked about before is there are some things that are actually not very good at dissolving and other things. This phrase right here, like dissolves like, refers to the idea that you need molecules that are similar to one another in order for them to dissolve. So you may have heard the phrase oil and water don't mix. And I have a picture of an oil molecule right here and a water molecule right here. Why don't they mix? Well, the oil molecule tends to be nonpolar. Straight chain hydrocarbon compounds, and water we know is polar. So when we say that they don't mix because they don't have very similar intermolecular forces, and the strengths of those intermolecular forces are very different. So water, is held together by hydrogen bonding, which is a strong intermolecular force. But oil molecules, being those long straight chain nonpolar molecules, only have London dispersion forces. So what we see is that essentially the water molecules don't, at least for a long time, let the nonpolar oil molecules penetrate into that network of hydrogen bonding. It's just it would be very difficult for that to happen because they have such different intermolecular forces available. So you might say, well, what about on that previous slide, Mr. Lyle, a couple slides back, where you were looking at CO2 dissolved in water? CO2 is nonpolar and water's polar. So why are they able to make a solution? Well, think about this. You don't really actually see CO2 dissolved in water except under very special conditions. We see CO2 dissolved in water when, for instance, in a soda bottle, but we have to put that soda bottle under high pressure. And what happens as soon as you open the bottle? The CO2 starts to fizz out. It starts to escape the solution. So it's actually not a really great combination for producing a solution. So when we say like dissolves like, typically, nonpolar substances will dissolve very well in other nonpolar substances. Polar substances will dissolve very well in other polar substances. And water molecules, which are polar and have, a positive and a negative end, are really good at dissolving ionic compounds because they are also charged. So what we're going to do today is pause on the videos and talk about a few other properties of solutions. Earlier in first term, we got the solubility rules, where we learned that molecules are either soluble or insoluble in water. But there's actually a lot more to it than that simple kind of black and white. And so the first thing that we're going to do today is talk about the difference between having a saturated solution and an unsaturated solution. And in doing so, we're going to explore those ideas through a group POGL. So we're going to come back to class right now and have the work of a POGL help us to define these concepts of saturated and unsaturated. See you in a minute.